Thank you so much. You've seen the slide. This presentation is called PEP 683, Immortal Objects, a new approach for memory management. A little bit about myself. For those who never heard about me, my name is Vinícius Gubiani Ferreira. I am from Brazil. I work at Asion Technologies. It's a serverless edge computing company. I just became a tech manager at Asion like 3 weeks ago. Didn't have much time to change that other picture of the guy with the scissors, because before I was a manager, I was a QA team lead for about 2.5 years. So I think that image passes as I feel about quality itself in code. And before that, I worked as a back-end Python Django developer for about almost 3 years and something. I like to work on open source projects. The most amazing project that I worked in is translating the Python documentation for Brazilian Portuguese. And I also love craft beer. My favorite one is Weiss. If you know where can I get a Weiss beer around town, please let me know. And ride a bike around my park, a park in my town. Don't even know a bike myself. I rent it per year, so it's easier for me than doing maintenance. So our schedule for today, we're going to talk about memory, of course, like it's in the very first slide, like from the basics, Python objects, garbage collector, GIL, threads, processes, how they all relate. Then we're going to talk about the motivation for this PEP itself, why it was created. Then problems that arise when implementing this PEP. And after that, a brief into what's next in the future, into how this Immortal Objects thing can actually be used in the future in other changes in Python. So let's start from scratch. Memory from the basics. Like everything in Python is an object. And if you don't believe me, I'm going to quickly demonstrate by using Python, of course. If we ask Python, is the number 42, the meaning of life and everything else, an object? Turns out, yes, it is. And you can do the same question for an empty list, a type, such as float, and even methods like the upper method in strings. They are also objects. And the other variations of methods, like anonymous functions, are also objects. And even the isInstance method is also an object. This is quite interesting. Like you use isInstance as a parameter for itself, and it gets true. But what exactly is an object anyway? So without a ton of C code to explain, it boils down to something like this. Let's say we have a variable, a equals 50, and then we need to think of it as something, in this case a, pointing to a value, in this case 50. And this can actually be represented by that structure on the right, which has 3 main properties: a type, an integer, a value, 50, and a reference count, like how many things are actually pointing to this value 50. And this is like the simplified version. Just in case you want to go for the nightmare version of what I just explained, follow this link. It will take you to the CPython repository, and then you can have a lot of fun, much beyond this very, very simple explanation. But now let's try to create some extra objects. Let's say we have A equals 50, B equals A, and C equals 50. And we will use the ID method just to check the memory position of these objects. And something funny will show up, like they will all have the same memory position. So what's going on over here? Turns out that Python didn't really create 3 new objects. It just reused one existing object and pointed these names, this A, B, and C, to the very same object. So the reference count for it is actually 3. 3 things are actually pointing to it. We can also use the is operator to double check that they are all the same object. Now, let's go the other way around. Instead of incrementing the reference count, let's try to decrement it. Let's say we set A to none, B to false, and C will be the very last thing that's actually pointing to the value 50. So all of them, we have the reference count as 1, and we'll have different memory positions. In practice, it won't exactly be 1, the reference count, but we'll get into that in 2-3 slides ahead. And we can even push even further, like using the delete statement for actually removing the reference that C was actually pointing to the value 50. Now, nobody else is actually be pointing to 50, so the reference count is actually going to reach 0. And then the garbage collector is going to kick in and grab the memory, release it back to the operating system. So garbage collector in Python is the mechanism for actually releasing the memory, so you don't like drop your whole operating system. And it can kick in one of three possible ways, like when a variable is reassigned, when it gets out of scope, like exiting a method, or explicitly calling the delete, like we did over here. And here's some sample code that you can actually use to check how many references you have for anything in your Python code. And you can use either this or the sys.getHalfCount method, but I actually prefer this one because the getHalfCount actually creates a reference and gives you the wrong number, so you actually have to decrement it by 1. So this is actually a better approach, gives you a clean approach, the exact number that you have. And I mentioned about 2 slides ago that if you try to do this for some values such as false, none, etc., then you may get some weird, unexpected results. So this is actually because the Python interpreter is booting up when it is loading. It sets a lot of references to some particular variables. So you might get unexpected results depending on the Python version that you have. Now, let's talk about CPU. Let's say we want to speed up our code as best as we can. And we mostly have 2 good options available, which are threads and processes. Threads are lightweight and easily share memory. And processes, on the other hand, like are bulky and have a bit of a hard time into sharing memory, but they are more isolated. There are other ways, such as async I/O and distributing jobs across the network on different computers, but they mostly boil down to these 2 over here, threads and processes. And what's the issue with objects when trying to share in threads or processes? It is possible for a mistake to happen in the reference count field, and it actually never reaches 0. So we end up having what's called a memory leak, a memory that is never returned to the operating system. And we'll discuss with more details in a couple of slides ahead how this can actually happen and why is this such a big problem. All right, so after this brief introduction, let's talk about the PEP itself. PEP 683 was actually created by Meta inside Instagram, and they had 3 different reasons for creating this PEP. They had issues about CPU cache invalidation that they wanted to reduce. They also had issues about data races condition that they wanted to avoid. And finally, they had issues about copy on write, or just cow in some other places where it appear, that they also wanted to avoid. So let's discuss each one of them individually. So cache invalidation. In order to improve performance of the code that is actually running, the CPU actually likes to cache data near its memory, like L1 and L2. So just so we won't have to go to the main memory, to the SSD, to the hard drive, to fetch it again. And for constant object that doesn't change, this should stay in the cache memory for a really, really long time. However, there is a bit of a problem with Python objects is that if you create a new reference, that actually changes the reference count. And unfortunately, destroys the memory, invalidates the memory that is in the cache, and the CPU needs to go back to the main memory and get that object again and keep it on the cache. So if we really, really had immutable objects in Python, this wouldn't actually be a problem because then the reference count wouldn't need to change, and we will have a slightly quicker code in execution since we wouldn't need to spend another cycle into going back to the main memory. And talking about data races when we're actually sharing objects with different threads and processes. Python is not actually considered a thread-safe language, so it is possible for mistakes to happen. And as I mentioned before, like the reference count code never reached 0, and we have to deal with that. So this is what we should expect the code to happen. Let's say we have an object which is shared with 2 different threads. So the reference count for these threads for this object, is actually 2. And both of these threads are done with this object. And they're gonna, like the first thread, release the reference count, just decrement from 2 to 1. And sometime later on, the second thread is gonna do pretty much the same thing and decrease it to 1, from 1 to 0. And since now it actually reached 0, the garbage collector is gonna once again collect this memory and release to the operating system. So everything is fine, everyone is happy, and life goes on. Now let's discuss what does when it doesn't happen quite that way. Let's say we have the same scenario where we have a Python object. It is shared with 2 different threads, but they are done with the object and decide to release it at the same time. So the first thread is in the process of actually decrementing the reference count. and all of a sudden gets interrupted by the second thread. It is waiting. And now the second thread decreases the reference count from 2 to 1 and gives control back to the first thread. And now the first thread is actually going to continue on where it was, but not decrement the reference count from 1 to 0. It's actually going to decrement from 2 to 1. And what's the problem over here? This reference count will never, ever reach 0. And now we have a memory leak. Thank God, at least we have a solution for this. It is our very good friend, the Jill. Nobody likes the Jill, right? Yeah, that was an awful joke. But unfortunately, the Jill solves this problem, but it locks up the Python interpreter. It doesn't allow us to do multi-thread with different cores inside Python. At least it didn't. Like, we had some changes recently that kind of allow us. And if we had truly immutable objects, this was not a problem, the reference count field. Like, this value is constant, it's never going to change. The reference count doesn't matter anymore. Then this wouldn't happen. We wouldn't have to care about that. Hold that thought. We're going to go back into that a couple of slides ahead. And this is particularly, I think, the most interesting case that Instagram decided to work on. It's about copy on write. So a bit of context over here. Instagram, they actually use a pre-forking web server architecture for their Django application inside Instagram. And what exactly does that mean? It means that they have a master process, and that processes end up spawning other child processes, and these child processes are the one that receive requests, incoming requests from the clients, and handle whatever they are looking for, like images, posts, text, whatever. And for each child process that is started, they actually receive a copy of the parent memory, but it is shared with them in a read-only state. And they had a lot of memory, which is supposed to be constant. It's going to be the same thing throughout the whole execution of the program. It's not supposed to change. But unfortunately, like almost all operating systems, they work on a copy-on-write scheme. What exactly does that mean? It means that if I want to change this memory that was shared with me in a read-only state, I must make a copy of it. So that's the name, copy on write. Makes sense, right? I never knew about that. I discovered this when making this presentation. Didn't understand. And the situation was, they had a lot of memory that was supposed to be constant, but turns out it was not. They measured it up and they found something really interesting, like the number of requests were going up in the right direction, and the memory usage was supposed to be a lot of constants, and the memory usage was still going up. And at the same time, the shared memory, which was supposed to be near to constant, was going down. Like for each new request, going down, down, down. And this is really interesting. Like, does anybody have a clue what's going on over here? It's not worth a book yet. Go. What? Not quite there. It is near, but not. Anybody else want to take a guess? Yes. Yes, it is. Unfortunately, what was going on? Like, you're sharing objects with different processes, and they are supposed to be constant. But unfortunately, for any new reference that you make into another process, it ended up creating or removing a reference. And unfortunately, that object that was supposed to be constant, it was not, because the operating system unfortunately disagreed with us. And here's a more practical example, just in case somebody didn't get it. Like, let's say we have this object. We created 2 child processes. So each one is actually keeping a reference for the object. And now, let's say one of the child processes is done with this object. So it's going to change the reference count from 2 to 1. And this is like supposed to be a constant. And I'm going to ask you, did this value of 50 changed? It didn't, right? But unfortunately, this operating system disagrees with us because it looks at the whole object, not the value itself. So this is like the tricky part for anybody who's coming from Java, from JavaScript, from, I don't know, COBOL, coming new from IT or any whatsoever, doesn't have a clue what the garbage collector is, reference count, the GUI itself. It's going to look into that very cool line over there. Oh, A equals 50. Did this value change? It did. Under the hood, it changed. So that is awful. And what the engineers inside Instagram wanted to achieve, they actually wanted to achieve truly immutable objects. But before we get any further into this presentation, we have to make some common ground over here. They wanted to achieve things that are truly immutable, but they ended up calling it immortality, or immortal objects. And why is that? Probably because the name immortal reminds us of something that will live through the whole start of the program until the very end. Also, probably not to make any confusion about things that are supposed to be immutable, like strings and tuples. And by the way, I have news for you. They lied to us. I've been lying my whole life. Strings and tuples are mutable. If they tell you otherwise, then they are wrong. Like, you can change the reference counts, so they are mutable, let's call, but you don't like to discuss that in a job interview or any kind of stuff. And probably like maybe immortal objects. That is a cool name, right? At least I think so. It's great saying like immortal objects. What is that? I'm coming to this presentation. Yeah. So this is where I get to the nasty part of this presentation about the C code. There is not much C code, but I'm going to do my best over here. This is a short, brief representation of what a C object looks like. We have over here like the reference count field and the object type. There's also the data part, which is not over here just for the sake of actually making it simpler. And what they decided to do is set this reference count field to a really, really, really high value. So when you get to this value, this will be like an immortal object. And then the reference count field wouldn't change it anymore. And what value is that? Is that really high value on the top right over there. I'm not going to even try to read that because I'm going to be ashamed over here trying to read that. It looks like a magical constant. It is not. It's very specific. You get that value when you set all the lower 32 bits. And this is a print screen from the CPython implementation. You can also see the definition of the immortal constant at the end, in line 110. And what they also had to do, they also had to ensure that the increment and decrement part of the code for the reference count field wouldn't change anymore if you're actually dealing with an immortal object, because you reach that value, it is not supposed to change it anymore. So you can see that on the first line of each macro over here, it is an immortal object. Yes, it is. Do nothing. Just keep it. Some examples of immortal objects that I've seen are like values that comes along very often in Python code, like none, true, false, empty string, small integers. And of course, inside the Instagram, they probably have like specific objects that are most like particular to them, and they mark it as constant. They reuse it a lot just for the sake of actually saving up memory. And what I got after these implementations, like they noticed that the number of requests as it kept growing, they are using less memory, and there are more shared memory, like on a higher level. But most important, like for the first time in Python from 3.12 forward, we had truly immutable objects. And why is this a big deal? Because we're actually bypassing the reference count, the garbage collector, and most important, the GEO. Like this object is now greater than the GEO. You can share it with anyone you like, threads, processes, somewhere and across a network, doesn't care. It's going to be surviving everything and everyone. So that's great, right? Except we have problems ahead. So keep calm and carry on. The issues they had to work on were mostly like working about backwards compatibility. So like making sure the Python application wouldn't crash, because we're not actually dealing with Python code over here, we're dealing with C code. And anybody who has programmed in C knows if you just look at your program, it's going to crash, like it didn't like your face, that kind of stuff. They also had to worry about accidental immortality, and that is a real thing. It actually can happen. Like you just set a lot of variables to any specific value you'd like, and then the reference count is going to start incrementing and incrementing. So you just keep doing that, do it a lot. And after that, you're going to reach that really, really high value you saw before, and then you have an immortal object. Luckily for us, it takes about 4 or 5 computational days just to get to that value, so we're safe. They also had to worry about platform compatibility, which means like getting this working into different operating systems like Unix, Mac, Windows, different architectures, 32, 64 bits, ARM, what else? Different compilers such as GCC, CLang. And most important, they also had to worry about performance degradation. You notice that I mentioned about the Py increment and decrement macros. Like, this is like the hardest part in the Python code. If you're doing pretty much anything with Python, you are passing that part of the code. And there are other places that they change it. And of course, this is like a simplified representation over here during this presentation. they measured it up, and it got worse in Python by roughly around 2%, which is fairly acceptable. Like you win in memory, but lose in CPU. It's a kind of a trade-off. So now let's talk about where Immortal Objects can be used. I'll show this graph before. I'm going to show it again because I find it pretty amazing. Like you're going to have a lower consumption in memory when you're doing parallel processing on a scale. If you have a lot of requests coming in and you have constant memory, then you're going to consume less memory. But once again, most important, you're actually going to be able to bypass the GEO itself. Like these objects are greater than the GEO, so they survive. And there are two PEPs, at least, that I know that considered using Immortal Objects. The first one was PEP 684, a pair interpreter GEO. It was presented on PyCon US 2023, I believe. It's really great. And the other one is the big one, the one of the moment, PEP 703, making the GEO optional. So I'm going to quickly discuss each one of them over here. PEP 684, it has the objective of actually running parallel code into multiple cores. And who's the guilty over here that we can't do parallel processing? Anybody have a guess? It's in the slide. Here's a tip. The GEO, yes, of course, the GEO. Is the GEO a villain? I don't think so. At least I like to think that he's the guy that lived long enough and unfortunately became a villain. And why is that? He actually allows us to not, I don't want to handle semaphores, that kind of stuff, data races, conditions, so we're fine. But unfortunately, he's actually holding us back and preventing us from doing multi-core parallel processing. And what this PEP actually did, it created the idea of subinterpreters, and it takes the best of both worlds, like using threads, lightweights, and processes, isolated and completely safe. So this PEP actually did stop sharing the GEO when you're using subinterpreters. It used isolated interpreter execution. We had for a while that. Also isolated interpreter state, still going on even after this PEP was actually closed. And reduced the number of global variables. We had over 4,000 of them in the code, and now I think it's around 2,000 something, not sure about the exact number. And I had to bring this up because I found this really amazing. I had a feeling this PEP was actually never actually meant to be taught because this says how to teach this, and I found it really amazing. Like, in addition to PyNewInterpreter, you also have PyNewInterpreter from config. Kept reading on, and I found that this PyNewInterpreter from config is actually a struct in C with a field on GEO. You set it to true, you get yourself a new isolated GEO, and you set it to false, you get just the plain old Python as it used to be like from Python 3.11 and backwards. And to wrap it up, this other PEP over here, PEP 703, making the GEO optional. So this PEP actually considers the idea, yes, we will have what we've been discussing so far, immortal objects such as true, false, none. So these guys will actually stay alive for longer than most objects. It will also have the idea that, yes, we will have to change the PyIncrement and PyDecrement macros for doing nothing on those immortal objects. So you're probably wondering, oh, great, this is actually going to use PEP 683, right? Turns out it is not, because the objective of this PEP is actually making the GEO optional. So the people involved, they decided to go for a different implementation. Instead of actually reusing a field, they decided to add a new field. So they actually ended up with different bit representation for marking immortal objects. So this PEP has mostly three main parts, which is immortalization, what we've been discussing so far. It also takes the idea of deferred reference counting, which, if I got it correct, is like postponing releasing memory for methods and modules, because they will be changing a lot and very often, so we'll actually use cyclical reference counting instead of the usual garbage collector way. And it also creates the idea of bias reference counting, which I got it correct is like saying who's the current owner, which thread owns the object right now, who can actually change this object. And my opinions about this PEP, this is not a big surprise. There's going to be two versions of Python, one with the GEO and another one without it. It'll be slower, a lot slower, like depending on which CPU you're actually using, 5 to 8%, so you have to measure it carefully just to see if it's actually worth using it. There will be a lot of code that needs to be recompiled, and there will be a lot of code that is not thread safe that will show up, unfortunately. So here are some references if you want to check it out further, going to this, the second link, I think it's the most useful one, is like the actual implementation of the Immortal Objects itself. Just in case you like C code, you can follow this link and you probably have an awesome time. So if you have any questions, you can look for me into any of these social media, email, etc. I'm not that active on social media. Thank you so much for staying until the end. Thank you. Obrigado. Gracias. Gracias.
Okay. Thank you, Vinícius. We have questions on Slido.
Yeah.
I want to read it for you. What is a good use of Immortal Object into a Django project?
In a Django project, let's see. This particular case for Instagram, their web server is like a Django application, and they use it just for the sake of actually reducing the number of memory because they're using. They have, I don't know how many requests. I'm probably going to say like millions and hundreds, that kind of stuff. So this actually reduces the memory that is being used. Is that person in the room?
No.
Oh, congratulations, you get a book. Thank you. Have a nice reading.
What is a good use of Immortal Object into a Django project? Oh, this is the same?
Is it the same?
Ah,
Yeah.
okay. Are Immortal Objects protected?
Quick, before anybody. Go, sorry.
Are Immortal Objects protected from being deallocated?
Sorry.
Are Immortal Objects protected from being deallocated?
Yes, they are. They are essentially a memory leak. Like, they're only being deallocated when, in two occasions, like when you deliberately close your application or when the application crashes. Essentially, they are a memory leak. Like, you're causing a memory leak on purpose just for the sake of instead actually allocating memory and deallocating memory and wasting CPU and sometimes even using more memory than you should. Like, you just allocate memory once, and that's about it. You go until the very end of the program. Or when you restart it, crash, that kind of stuff.
Okay. What tools or techniques do you recommend for identifying and resolving memory leaks in Python applications?
I didn't get it, sorry. What tools or techniques do you recommend for identifying and resolving memory leaks in Python application? Wow, that's a good question. I'm not the best expert in profiling. I would recommend, I saw a workshop about memory array. That's correct. Somebody been to this workshop during the conference. That is a tool that can be used. There probably are other tools to manage memory to check if its memory is actually leaking. Usually, like when memory starts to go increasing, and without stopping, there is a possible way of finding a memory leak.
Memory is also a tool for that.
Memory. Sorry, I misspelled the name of the tool.
Can you explain how to mutate an immutable string?
Strings, they are said to be immutable, and they are like, you can't like add a new letter in the middle of a string, like trying to change, like for example, position 3 of string. That's going to give you an error, but you can't actually you can change like the reference count of that string. So it is mutable and not mutable at the same time, because you can mutate it in a lower level, in the C level, of how many things or how many names are actually pointing to that string. But changing the string itself, you can't do that. Python code is not actually going to allow you to. In CPython. That's cheating, not in Python. Oh yeah, but changing directly like the position of the string. You can't do that.
Okay. Will it be possible to create custom Immortal Objects?
Yeah, in the future, maybe. Right now, you can only do it at a C level. There is a question I got before, like right now, on a higher level, just using Python by itself, you can't. You have to like set it by using the CPython implementation. You can't directly, like in an application, set an Immortal Object. Maybe in the future, in a next release, who knows?
What's the status of the PEP? How likely is it to be accepted?
Could you go to the start of the question again? Sorry.
What's the status of the PEP?
I believe it is closed right now because this was actually delivered with Python 3.12. I think that is.
Is the garbage collector called once an error is raised?
For Immortal Objects, the garbage collector called once an error is raised. Actually, the garbage collector for Immortal Object is never called because the reference count never reached 0. The garbage collector is only called when for objects that have the reference count as 0. So this the garbage collector is actually every now and then being called, but for those objects it is not. It does nothing on them.
Why don't use atomic CPU instructions to avoid data races instead of implementing the GIL?
Why don't avoid? That is a good question. Yeah, I'm going to read the question again. Why don't use atomic CPU instructions to avoid data races instead of implementing the GIL? I think that might be particular depending on the architecture itself. So that'll be, might be wrong over here, might be a thing that is more specific to specific hardware types. So it's not like an implementation that you can use completely in Python itself. I'm not sure that is actually possible for all types of architectures. Might be something that is architecture specific. I'm not sure if I answered that correctly. It is an opinion. Yeah. As you mentioned, I'm going to repeat. That is not true for all data types in Python. For some, the more native ones like integer and float is likely, but for custom like a specific object or class, they're probably not. Yeah, I agree with you on that one. Thank you.
Okay. What is the relationship between interpreters, processes, and threads in the case of PEP 684?
Interpreters, processors, and threads. PEP 684, it actually created the idea of having an isolated interpreter with its own GIL. So let me check the question again. So you have a more isolated environment for running your code, and it's more safe regarding memory. Like memory is not going to escape each sub-interpreter. So you can do like threads and processes in a more secure and isolated way, in a way that is not going to spill over between different executions. Like you have a main processes, and from the Python processes you start different sub-interpreters, and each sub-interpreter is safe. Nothing can escape on it, except you explicitly tell it to. You can run it with the main GIL, but that doesn't sound like a very wise thing to do. Why would you do that?
What techniques does garbage collector uses to find quickly which objects have reference counter equals to 0? Because there should be a lot of objects in Python's memory.
Usually that is done like automatically every time in those three cases, like when a variable is reassigned, goes out of scope of a method or on the other execution, or automatically when it reaches 0. It's like it is triggered under the hood in the CPython code, at least as I read for this presentation. So it's not something that goes on continuous. Like if you halt your Python code, stop it in like a specific line with PDB, that kind of stuff, then the garbage collector will also stop. It's not going to do nothing.
How does Python's garbage collection is different from manual memory management in languages like C or C++?
As far as I know, I could be wrong over here, like managing memory in C and C++ is something like you have to do it manually, like by yourself. So if you forget to do it, then you are in big trouble. And Python does that for you like automatically. Like, so it's something that you don't usually worry about memory, except when you are having memory consumptions problem, like you're consuming a lot of memory, then you start to worry.
Last question. Can you explain further why we are safe in regards to accidental immortal objects?
Mostly because that number I mentioned before, setting the lower 32 bits, it is a really high number, and you need a lot of effort in the Python level itself. So either you have like a deliberate code that is actually trying to force that on purpose, or like I don't know, I'm sorry for my words, you're the worst programmer ever, like, to let something like happen, because how can you actually reach that really high number? I don't think a specific case that can actually happen. It is possible, but I think only on purpose. I'll never try to do something like that.
Thank you. That's it.
Yeah.
Thank you for.
Thank you.